Good morning, Mark.
Good morning, Tracy. Good morning, Godwin.
Morning, Mark. Well, it's already 5 minutes past 10. I think we can start. Others will find us, and whatever they missed, they'll catch up on YouTube.
Okay,
All right.
let me see. Are you able to see my screen?
Yes, yes. I'm able to see
Yes.
your screen.
I'm at the definitions, yeah? Is that
Yes.
Yes, you can go ahead.
okay? See. So, probability, still in statistics, is the likelihood for an event occurring. Do tell me when my time is out also.
Right.
From the slides, the definitions are quite clear. Low probability, that means there's a low chance, a rare chance of occurrence. An event is a collection of outcomes of a procedure. A simple event is one single outcome. If we have, say, I used a deck of cards a lot. If we have a deck of cards, the chance of picking maybe a two hearts is a single event. A sample space is the whole deck of cards, all the simple events. Yeah? Hopefully that makes sense.
Yes.
An example that I give is flipping a coin. So a coin has a head and a tail. If you flip a coin once, you always have a procedure, an event which we have defined, and a sample space. So if I flip a coin once, there's chances of me getting a head. That is the event we are looking for. So the sample space will be the head and tail. So your probability, you're trying to find the probability of getting a head, yeah? Which will be 1 out of 2 since your sample space is made of 2. If I flipped the coin 3 times, I would have this sample space. I could either get 3 heads, 3 tails, or heads and tails in different orders. They are all different because I could get a head first, then 2 tails, and getting a tail, head, tail is a different thing as well. So if I wanted to find the probability of getting 1 head and 2 tails, I would go in my sample space and pick out how many possibilities are there to getting 2 tails and 1 head. So then we have types of probability. Probability is either observed, classical, or subjective. Observed, you base it off an observation from an experiment. So if like that example above, flipping a coin 3 times, that is observed. I have carried out the experiment and I have actually observed how many ways I can get this, yeah? Are we still together?
Yes.
You can tell me to go back at any point you want.
All right.
So this is how you calculate it. Number of times A occurs out of number of times procedure is repeated. So it's driven by practical estimate, and it's based off real world occurrences you observed, because you're going to have to actually put this into practice to get a result. Classical is based off a chance of an event occurring. That means if it is a deck of cards, we know that we have 12 hearts, 12 spades, 12 clubs, 12 diamonds. So getting a heart and equal chances of occurring. That is how classical works. We know the chance of something occurring. So it's based off the chance of an event occurring. Each simple event must have an equal chance of occurring. So it's used in situations with well-defined outcomes, and they have equal probability of occurring. With subjective, you make it off an estimated guess. For example, say a doctor, if he looks at an individual patient, his past experience does not determine the diagnosis for this other patient. Just because 2 people have cancer doesn't mean they have equal chances of surviving. So you make it of an educated guess based off the circumstances. It's also very individual based. It's based off personal judgment. Then I have some examples. So the probability of selecting a heart from a deck of cards. This is very classical because we have not gotten a deck of cards and started counting. It's not practically done. We just know we have 12 or 13 depending on what type of how many cards you have in the deck. So if it's a deck of 52 cards, we have 13 hearts. So the probability of selecting a heart from that deck will be 13, the event, out of the sample space. Number of hearts in a deck out of number of cards. Another example from the classical probability is the probability of having 2 boys among 3 kids. So assuming a couple had 3 children, and we wanted to find the probability of them having 2 boys among the 3 children. We are going to create a sample space. So they could either give birth to a boy, 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 or have a boy, boy, girl, and different orders of, they could be the same outcome but different orders. That is still a different event. Then we look out for the events that have 2 boys and 1 girl as our question specified. That is 3 out of the sample space, which is 8. Then examples of observed. The probability of getting 6 tails after flipping a coin 100 times. A probability of getting 64 tails. This means someone actually flipped the coin 100 times and got 64 tails. That is why it is observed, because it was practically done. So that's simple. You just get the 64 out of total number of times the procedure was done. Polling. Now imagine a poll was organized and they asked people if they agreed with cloning or did not. So we had 91 people who think cloning is good, 901 people who think cloning is bad, 20 people who have no opinion on our question. So, what is the probability of selecting a person who thinks cloning is good? First, you get the total number of people on which this experiment was carried out, and people who think cloning is good were 91. So, 91 out of the total number of people will give you the probability of actually picking someone who thought it was good. Subjective. Subjective, we said, was of personal judgment because different experiences happen to different people in a broad aspect. Everyone experiences something differently. So the probability that it will happen to you is different from the probability that it will happen to me. Say a bird pooped on your car, like the example I gave here. My car could have experienced that more times than yours. So the probability I'll give you will be from my own experience, and so does your probability. This is why it's subjective, it is prone to change. Also, the probability that you'll survive cancer. I could survive, and someone else that has it may not. So, complementary events. These are events that are mutually exclusive, they don't happen at the same time. Say, rolling a die. If you roll a die, you can either get numbers 1 to 6, but you can't get 1 and 2 at the same time. They are mutually exclusive. And from the probability laws, the probability of something plus the probability of its complement is always 1. It's like the probability it occurs and doesn't occur. An example in case is rain. Will it rain or will it not rain? Adding the two will give you 1. Then we have the addition rule, but varies from what type of event it is. I started with compound event. This is an event which joins 2 or more simple events. So the probability of rolling 1 or 5 on a die. Take or is our keyword. So we can have one or the other or both. What's the probability of rolling and getting a 1, probability of rolling and getting a 5, or probability of getting both? So probability of A or B is equal to probability of A occurring or B occurring or both A and B occurring in a simple trial. Excuse me a bit. I'm going to take a call.
Yes, and Tracy,
Hold on.
I just wanted to inform you that your time is up. So everyone, as we wait for Tracy to conclude her phone call, our time is up. Hopefully next time she can repeat the addition rule because I haven't gotten that one clearly. Who else who would like to go next?
Yes, good morning, Bedouin.
Good morning.
Good morning, everyone. I would like to go next. Yeah.
All right.
So today I'm going to look at area under a curve and volume by revolution in calculus. So first of all, I'm going to look at numerical integration. We use it in estimating areas and volumes when the exact integral is difficult to perform. A common technique that we use is the trapezium rule. Yeah. Then the definite integral is denoted by the integral of f of x denoted from x, represented. Sorry. The common numerical integration technique is the trapezium rule, and the definite integral represents the area between the function f of x, the x-axis, x is equal to a to x is equal to b, a and b being the bounds. Sorry, there's a problem with my PDF openness. Yeah. Then here, if a function f of x is continuous, let's say it has no breaks, jumps, or gaps, and is non-negative for all points on the domain, on the closed interval a and b, the area of the region bounded by the graph f of x, the x-axis, and the vertical lines a and b, these lines that are generated from the bounds, is given by that formula, the expression. So here I'm going to talk about the trapezium rule, and this method works by dividing the area into trapezoids, or trapezia is it, and summing up their individual areas to get an approximation of the total area under a curve in those specific bounds. So using more trapezoids increases the accuracy of the area approximation and reduces the error for the unaccounted for area. And this method is applied when the function, sorry, there is missing word, when the function being integrated is difficult or impossible to integrate analytically. Analytically means we use like those different techniques by parts, by use substitution or what. And sometimes you encounter functions that do not have elementary derivatives. In such cases, you use the fundamental theorem of calculus to find the exact value of the definite integral. Yeah, so now here I have an example. Let's say a function y is equal to x squared from x is equal to 1 to x is equal to 4. This graph shows the area under a curve y is equal to x squared from x is equal to 1 to x is equal to 4, divided into three trapezoids, these ones that are represented in the darker blue parts of the graph. So now, in the example here, we have three trapezoids. The parallel sides are the vertical lines, these ones. And the distance between them, let's say the height, or the width, we are taking it as 1, yeah? So the area of the first trapezium is taken this expression. The formula of area of a trapezium is a half times width into a plus b. A plus b are the vertical distances of the trapezium. So here we have the first trapezium, a half into f of 1, which happens to be this one, and then plus f of 2 times the width, which happens to be 1. And that's the expression. Then for the second and the third, we do Okay, we also work on the second and the third. Then the total area under the curve from x is equal to 1 to x is equal to 4 is equal to the summation of the areas of the graph that we've, sorry, of the trapeziums that we've worked out, the three of them. So here we have the formula of the trapezium. It's generated from the summation of the areas of the trapeziums, or the subintervals that we've generated from the area. It happens to be the area approximation, which is equal to a half times the width of the trapezium, denoted by h, times the first value. Okay, these are the vertical distances. The first value, which happens to be the y naught, plus the two middle y values. There could be more than two, depending on the number of subintervals. But remember, the more the subintervals, the more accurate, because you have to, okay, it minimizes error. You do realize that now, like for this first trapezium, there is this area between the, should I call it the, okay, between the red curve, yeah? In this trapezium, there is that area that is unaccounted for. But realize that if we are to have more trapeziums or more subintervals, this area is most likely going to be less, or it would be accounted for much better. Then here I'm going to look at area under a curve, but here it's exact integration. Exact integration is applied when the function can be integrated in a closed form, and it's more accurate than the trapezium rule. Yeah, okay, for exact integration, we don't have to deal with subintervals, because let me say, if we are to use the term subinterval in that context, they are to be, okay, the width between them, or their width, is taken to be tending to 0, or it's very small, so there could be very, very many, okay, a number of subintervals or a number of trapeziums, if I'm to use that term of, okay, yeah. So yeah, it's another common concept we've looked at before. And then area between two curves, or a curve and a line. The area between two curves, say y1 and y2, from x is equal to a to x is equal to b, is given by the integral of the magnitude, the difference between the upper and the lower functions. So using the vertical elements, the area is equal to the integral from a to b of the difference between the upper and the lower function, the magnitude of the difference, where y1 and y2 are the functions of x. And then also for the lower elements, or if you to use the horizontal elements, the area from C to D of the magnitude of the difference from x is equal of x2 minus x1, where x1 and x2 are the functions of y. Sorry, here.
Mark,
The Yeah.
Mark, yeah, I hope you can conclude quickly. Your time is up.
Right. We're still saying, okay, for area between two curves or a curve and a line, the region that is enclosed between two curves is the area between the two curves. So that's why we use the difference or the magnitude of the difference between the functions representing the curves. That's what we integrate. We first find the difference, then we integrate the difference. Yeah, then the key points are the curves must be continuous. We've talked about being continuous. It shouldn't be having breaks or jumps or gaps, and it should be non-intersecting. If they intersect, we must split the integral at the intersection points. And then the steps identifying the upper and the lower functions by sketching, let's see if it's possible, or evaluating y1 and y2 at different test points. The points of, we find, after finding the points of intersection, we split the integral, that is if they exist. We split the integral at the intersection points and then we evaluate the integral. So basically this is an example. This is an example of finding area bounded by curves. Here we have a curve y is equal to x squared minus 4, which happens to be this one. Then a line y is equal to 0.
Mark,
Y,
yeah,
yeah?
in interest of time, I think next time we can start from there. How to,
Right.
since we now know the methods, we can look at an example of how to actually use them from there next time. What do you think?
Yes, because the examples were like the next thing, yeah.
Yeah, next time we
All
can
right.
dedicate next time for examples.
Yes. All right.
So Ian, you're
More,
most welcome. Estienne, would you like to take over next, or should I
yeah.
take on?
Yes, yes, yes. Let me
Uh,
let me let me present.
all right.
Okay.
Yes. Try to compress everything under 10 minutes, but also don't move too fast that we don't understand.
I agree. Okay, okay.
So better move slowly and understand than rush through things.
Yes. This is yes. Okay. I'm presenting from where I stopped. Uh, from where I stopped. Anyway, I'm gonna pass through. Last time I didn't complete. Things were very many. So I guess you see my screen. Hello.
Yes, Estienne, you may proceed.
I go on. Yeah. Yeah. Auntie, I was continuing with Ngram models. Yeah. Now, I wanted the bad thing is that last time the presentation wasn't there, so I had some sketchy stuff. But today I tried to create something. So, as we had last time, an n-gram is a sequence of words, just a sequence of words. The n-gram is a sequence of words, of n words. So here I had an example of I am an engineer of, simply a sequence of words. Then the n-gram model. So the n-gram model assigns a probability to the likelihood of a next word in the sequence. So we get the probability of that word to come next in the sequence. But we base it on the already existing sequence or sentence. Then the applications have machine translation, whereby, as you see, like if you are translating from a language, let's say my language, Luganda, to English, it's more likely to have a sentence saying high temperature tonight than large temperature. because it makes more grammatical sense. Same, it's used in spelling correction. So you see about 15 minutes, note it has a higher probability than saying about 15 minutes, something like that. Then this for speech recognition, just like I'm speaking to you, if we are to write a text document from my words,
My meeting
it's
started
easy,
by
like
the
it's
time
you
I was
have
done
a higher
harvesting
chance of
bananas.
finding the word
We have
I
to ask
saw a
someone else
van
who's free.
than like I saw a van will sound will make more sense than eyes or of an. Then now this is where we start. We are calculating the probabilities. Since the entire N-gram model is a statistical model of natural language processing, it's statistics, so we are using probabilities. So I'm going to have to calculate the probability of a sentence or a sequence of words. So the formula is quite simple, whereby we say the probability of the sentence is equal to the intersection of all probabilities of all words in the sentence. I think you get me there. Like to get the probability of the entire sentence, you have to get the probability of each individual word and get the intersection of them all. Then, since our main focus was to find the probability of a next occurring word in a sequence, the next word to appear, then we are going to base on the probability of the already existing word. So the probability of a word in a sequence, whereby our word is WN, given, you have to find the probability of a word given the probability of all words previous to it in the sequence. So I found a few ways of calculating the probability, like 2 ways of calculating the probability. Well, the first one, it's the easiest, it's count and divide. We're going to use the example above, somewhere down, for about 15 minutes from town. But right now, count and divide. So if you are to get the probability of a given word to show up next in a sequence, given the sequence, you're going to get the count. In this example, in this formula, we assume that we have, let's say, a text document that we are going to give to our model. So the model is going to pass through all the sentences in the text document. Then it checks for a sequence, a specific sequence. Like for example, the example you have is about 15 minutes from town. So you're gonna get all sequences saying about 15 minutes from town, and we divide by all the number of times that about 15 minutes from appears in the document. So we have about 15 minutes from town divided the number of times about 15 minutes from town has appeared in the document divided by the number of about 15 minutes from has appeared in the document. There we'll be getting the probability of finding the word or the probability of town being the next word given the sequence of about 15 minutes from town. But as you know, there are many possible sentences in the more possible a sentence can be used in very many possible ways in a document or in the language itself. Well, that was one of the problems I saw. Then we can use the chain rule. So in the chain rule, you're going to use the conditional probability function, I think, whereby we're going to calculate saying if, like given, if we are to calculate the probability of B given A is equal to the probability of A intersection B divided by the probability of A. Then, since we have this, then that means that if we interchange, just interchange cross multiplication, I'm making A intersection be our making it taking it to the left hand side, we're gonna get the probability of A multiplied by the probability of B given A. So now if we take into account more variables, like more words, you're going to get the probability of A, the comma is the same sign for an intersection. So really not confused. The comma is the same sign as intersection here. That's why I'm using it. So I'm gonna say the probability of A, B, C, D, that sequence is equal to the probability of A multiplied by the probability of B given A multiplied by the probability of C given AB, such and such and such. So the chain rule in general, that's the chain rule. It stated that if we have x1 intersection x2 intersection what up to xn, you get the probability of x1 times probability of x2 given x1 times the probability of x. So that's the entire chain rule. And then now, since we are working with words, we have come to realize that if you sum up the chain rule, it will bring using the W means word. So the probability of a sequence having word 1, word 2, word 3 up to word n is equal to, this is the product of I. The I didn't come, unlikely I couldn't write it down, but it's a product of I, all I's, of the probability of W of I given all words before I, before that W of I. So that's what the statement, the first one, means. Then for our example, I have about 15 minutes from town. So about for 15 minutes from town, you get the probability of about multiplied by the probability of 15 given about, then multiplied by the probability of minutes given about 15, then and so on and so on and so on. That's how you find the probability of about 15 minutes from town. Then, but there was I think an assumption, a guy called Andrei Markov created an assumption that instead of using the entire sentence, we can use just words that come before the sentence, the word you want to predict next. That's where the n-gram models come in. Like instead of using exactly n, because these ones above, they all use n. If you look through it, they all use n. But you can use a part of the words in the sequence to identify and predict the next word in the sequence. For example, like in a unit, so the models are very many, because the n you just put a number. So the 1 gram or the unigram, here we say that each word depends solely on itself. So each word has a probability. Yes?
Yeah, just a reminder, your time is up.
Well, let me pass through here. I think I'm left with 2 slides. Just 2 slides.
Okay.
Right. So the unigram, each word depends on itself. For the bigram, each word depends on the word exactly before it. Then for a trigram, we use 2 words before it. But as you know, if you are using that, I'll have a hindrance of using n-gram models. They are simple to use, but they have a hindrance because languages, when you're writing a sentence, we can have long dependencies. Like the statement below, the computer which I had put in the laboratory on the first floor crashed. So if you take just the word to predict the word crashed, if you have to take flow, it's very hard for you to land on flow on crashed. If you take just fast and flow, that's a trigram, it's hard for you to predict crashed still, because the only word that could come to the only word that could bring meaning to the word crashed would be the computer, which is very far from the from the word we're trying to what to predict. But still, then went into biogram, yeah, estimating biogram probabilities. So estimating biogram probabilities, we use the chain rule. It would have been the chain rule, but here we're gonna say the probability of a word I given a word before it is equal to the summation of the occurrences of is equal to the occurrences of that sequence, the word before it and the word divided by the occurrences of the word before it. I think I have an example here, a simple one. I am a Dryas, then there are there are three sentences. I am a Dryas I am, and I don't like green bugs. The S is a special symbol to show a start of a sentence. This is just in case, like we have I, the first sentence, I is the first letter, no, is the first word in the sentence. So not to bring I think if you don't like the biograms would, let's say the model would work inefficiently with like I because it has nothing to precede it, something like that. And so S, this one, it just shows the beginning of a sentence. Then the last one with a slash shows the ending of a sentence. So with these three sentences, if we were to predict, now this is the probability of I coming after Dryas. So if you look into the three sentences, you find that Dryas comes, the sequence of Dryas and Dryas I is only one in the second sentence, but I comes, but Dryas is in two sentences. So it's the probability of the sequence, which is Dryas I in the second sentence, and the occurrence of Dryas, which are two. That's a half. Then the probability of am coming after I is you check there is I am is twice in the sentences. It's only twice in the sentences, but I comes three times in the sentences. Same thing, the probability of do I. But the probability of do given I, which is I do, if you read it, the probability of do given I is, you see that there is only one I do in the three sentences, but there are three I's. So that's just how you estimate, simply, that's how you estimate the biogram probabilities in the in a text document or in the data given to us if we are to use a biogram. So in the interest of time, I think I'll stop there. We'll start from there next time.
All right. Thank you, Estienne. We have two presentations left. That's me and Ian. I think I'll go next. I'll do my best to make sure it is under 10 minutes. I hope you're all able to see my screen.
Yeah, we can see it.
All right, thank you. So last time I'd said today I'll be going through Gaussian elimination and row echelon form when solving a linear system of equations using matrices and vectors. So let's take this simple equation. Let's say minus 3x plus just a moment. Let's take this one instead. This one should give us cleaner. Hopefully, it will give us clean answers without fractions. But although there can be fractions, So today, what I'm aiming to look at is how the principle behind how we can carry out a Gaussian elimination. Let's have this is 5z equals to 6 for x plus 3y. This is a minus, that's a minus 3z equals to 1 minus 6x plus 4y minus 7z equals to 3. So this is our linear system of equations. And we're going to look at how we can carry out Gaussian elimination. First of all, we write this in form of, they call it an augmented matrix, whereby you have the first part of the matrix. This is the coefficients of all the unknowns. Have a 2, 4, 5, 4, 3, minus 3, minus 6, 4, minus 7. Then we draw a line here and we have this value. We have the answer values. So this is an augmented matrix. It combines the matrix from the coefficients and the vector the vector answer that we get. So the objective of elimination is such that we get this part of the equation remains the same, 4, 5. This becomes a 0. This becomes a 0. This a 0. And whatever values we will get here after carrying out the elimination. Then also this remains the same and these ones change. So the objective of Gaussian elimination is to have these parts of the equation as zeros. And then in row echelon form, these three remain zeros, but these become ones. These are zeros, these are ones. These four, these ones usually change after we have transformed it into row echelon form. So let us see how we get from this. Let's see how we get from this to this by carrying out Gaussian elimination. Basically, to turn this into zeros, we subtract rows. Let's call this our row 1, row 2, and row 3. You subtract each of these rows from each other such that these become zeros. So let's start by making this a 0. To make this 4 a 0, we have to subtract equation 1 from this. We multiply r1 by, not by 4, we multiply r1 by 2. So we have 2r1. Oh, yes, we are subtracting. Okay, you can subtract and add. So we have r2 minus twice r1. And that will turn this into a 0. The first row remains unchanged. That's 2, 4, 5, 6. That remains unchanged. Then we start carrying out this operation. Twice of row 2, row 2 minus twice row 1. We have 4 minus twice 2, that is 4 minus 4. We have a 0. That's a 3 minus twice 4. That gives us, this is an 8 minus 5. That's a minus 5. So this gives us a minus 5. Feel free to unmute yourself and ask in case you don't get any don't get any parts. So then we have this. We have row 2, which has a minus 3. Minus, we have twice 5. That gives us twice 5 is a 10. That's a minus 3. minus 10, that gives us a minus 13. So this becomes a minus 13. And then we also carry out the same operation on the answer vector. We have R2, which is a 1, R1, which is a 6, and we have to subtracting twice R1. So minus twice 6, that gives us, this is a minus 12, 1 minus 12, that's a minus 11. That gives us our first zero. This is minus 6, minus 4, minus 7. Remember, our objective is to move from this to having these three as zeros, and we have our first zero. To get our second zero, let's make this a 0. This is, we also use row 1. That's our row 1, row 2. Then this is row 3, which is this. So to make this a 0, while subtracting, we have to multiply, that's row 3 minus row 3 and the minus 6. Which value can we use here? Let's see. I think that's a minus 3. Minus 3 row 1. I don't know. Is that correct? If we multiply these two by minus 3, do we get a 0? Oh yes, we do get a 0. So the first row 1 remains the same. Now, row 2 remains the same since we're working on row 3 and we're working with row 3 and row 1. This is 0, minus 4, minus 13, minus 11. Then row 3, we have minus 6, which is this, minus negative 3 times 2. That gives us a 0. So we get the first value as 0. Then we do the same for the remaining values. That is 4 of row 3 minus 3, 4 from row 1. That gives us, this times this, that's a minus 12. Minus 12 times this negative, that's a plus. This is a 16. Then we have 13. We have minus 7 and 5. Negative 7 minus 3 or 5. That gives us negative 3 times 5, that's negative 15. Negative times negative, that gives us a positive. That is minus 7 plus 15. That gives us an 8. Then finally, we are looking, oh, I forgot to include the value here. That was a 3. So now to get the new value here, we have row, yeah, it's first row 3, the value from row 3. From this, we have 3 minus negative 3 into 5. Oh, no, that's a 6. We're working on this, not this. Negative 3 times 6. Negative, that's 18. Negative 18. Negative times negative, that's a positive. 3 plus 18 gives us a 21. So up to this point, is everyone on board with what we're doing? I hope you guys are able to get me. I'm not sure if you guys can hear me. All right.
Done.
All right, let's proceed. So we have made this a 0. We have made this a 0. Now, up next, we have to make this a 0. We have made this a 0. This is 0. And now our next object is to make that a 0 to reach our final form, which is that. Next, to make this 15 a 0, we subtract. We have a row 1, row 2, row 3. We subtract row 3 and row 2. We have row 3 minus, let's see what value you can multiply this by, 4. 4 row 2 to give us a 0 here. Then we do the same operations for all the other values to make them consistent. We have a 2, 4, 5, 6. We already made that a 0, made this a 0, got a minus 4 here, got a minus 13, minus 11. Now we carry out operations on row 3 using this. We have our row 3 value, which is 16, this value, minus 4 times the second row value, which is a minus 4, to give us our new row 3 value. 16 minus 4 times minus 4, that gives us a negative 16. Negative 16. Wait, this gives us a plus. That means I was supposed to multiply this by a negative, such that we make this 16 as 0. So our row 3 value, 15, minus negative 4 into our row 4 value, which is a negative 4. Negative 4 times negative 4 gives us a positive 16, and this gives us our 0. So yeah, now we have made this 16 as 0. So we also carry out the same operation for the remaining areas such that they are consistent. Our row 3 value, which is 8, minus 4, or minus 13. When we multiply this, let me open my calculator. That is 8.
52.
Yes,
52.
52.
Mhm.
All right. So our value here becomes a 52.
No. 52 just by multiplying 14 minus.
Oh, so this is 8 minus
4 times.
52.
Yeah, 52.
So this
Getting
minus
negative
this gives us a 46.
46. Negative.
Gives us a negative 46. Okay. Then we carry out the same operation for this 21. Let me just erase this to create some space. So we have 21 from row 3. Oh, that's the 24. 21 from row 3 minus 4 of minus 11. This gives us 21 minus, this is a positive 44. And that gives us that 20, negative 23. So that's basically Gaussian elimination. moving from this such that we have these three values as zeros and carrying out the necessary operations to make sure these values, this remain consistent. So moving from this to that. And that's what we have done here. We have moved from our augmented matrix to having these three as zeros. Now, our row echelon form, now from this point here, we can simply transform this back into our normal equation where we have 2x plus 4y plus 5z equals to 6 minus 4y plus minus 13z equals to minus 11 minus 46z equals to minus 23. Then from this you can, from this last equation, if you observe, you can easily get the value of z. Then we substitute it into this to get y. Then we finally substitute it for these two. That would be back substitution after carrying out the Gaussian elimination. But we're interested in moving from this to the row echelon form. Which is this. The row echelon form, we have these three as zeros, but we also have these as ones. So basically, we after replacing these in our equation with zeros, we also replace these with ones. Our equation, this, let me just move this to a cleaner space. So this was after applying Gaussian elimination. Now let's turn it into row echelon form. To turn this into a 1, we multiply row 1 by a half. Then to turn this into a 1, we multiply row 2 by minus a quarter. To turn this into a 1, we multiply row 3 minus 1 out of 46, row 3. And that gives us 2 times a half, that's 1. 4 times a half, that's 2. 5 times a half, that's 5 out of 2. 6 times a half, that's a 3. 0 times a half, 0 times minus a quarter, that remains a 0. This becomes a 1. Minus a quarter times a 13, that's 13 out of 4. This is 11 out of 4. This remains a 0, 0. When you multiply it out of a 46, this becomes a 1. This becomes a minus 20. This is 23 out of 46.
Becomes just 2.
It
1
becomes
over 2.
just
1
1
over
over
2.
2. So that's a half.
Mhm.
Yeah. So basically now we have turned this after performing Gaussian elimination on this equation. Now this is the row echelon form of the equation. From here, when we transform these into our equations, we'll have z equals to a half. Then also once again, we can easily substitute this z into the next equation, which will be y equals to, that will be y plus 13 out of 4z
Mhm.
equals to 11 out of 4. Yeah, we can substitute this into this, and we'll get our z value. The row echelon form makes it such that we directly get our z here. But today's main objective was how to move from our linear equation to an augmented matrix, from our linear equation to an augmented matrix, from the augmented matrix to the performing Gaussian elimination on the matrix. Then finally, from this, after Gaussian elimination, to the row echelon form. What's most important is you know how to perform those operations. So yeah, that's how what I had for you today. How to perform operations to move from a normal equation to Gaussian, row echelon, and finally row echelon. Uh, if there are no questions, Ian, you may take over.
Thank you, Godwin. I like that. And I'm going to look in more on YouTube. I'm going to rewatch this. So let me present in under 10 minutes. Okay, hopefully you can see this. Yeah, so so this is a controlled NOT gate, and last week we covered the Hadamard gate. So we now know a level of quantum computing built with single qubit systems.
Ian, I don't know if you're speaking, but we can't hear you.
And
Justin, are you able to hear Ian? Ian, I'm not getting you.
Good.
Yes.
It seems Ian has extremely poor internet.
Well, I'm not really sure how we're going to now go about that.
Well, because he has been on and off, and since he's off right now, I think we can conclude from here. We'll start from there next week when he has better internet.
All right. Oh, but before you go, I wanted
Mm.
for the YouTube,
Mhm.
do you think it's necessary to split up the different sections of the videos and put them as independent, or I just put chapters in this one and people can easily skip to the area they want to watch? I feel like the chapters has low effort, but
Yeah, you just put chapters because since there are gonna be multiples of different weeks, I think just put chapters.
okay.
So someone just goes to like a week, look through the chapters.
sorry about that. My network is very unstable here. Let me the presentation.
It's, the problem is your network is extremely poor at the moment. We can hear nothing. Yeah,
Yeah,
your
it
voice
is
coming and
bad.
Ian, do you suspect your network will stabilize or we postpone to next week?
If it stops again, then we could postpone.
all right.
All right.
Right. So yeah. So what is entanglement? We covered that at the beginning. We talked about the three concepts: superposition, entanglement, and we said superposition is being in two states at the same time. But what about entanglement? So here, if you just read from this side, they're saying one of the foremost phenomena of quantum theory is quantum entanglement, the idea that particles of the same origin, which were once connected, always stay connected.
Mm.
Yeah, so it's a very important concept. It's like how one qubit is in touch with another. So when you have such a system, you can do very many things that the normal computers were not able to do. So back to this slide. Um, yeah, we now go to the next slide. So how do we create this state? We create this state with this CNOT gate. That it's called a control not gate. Yeah, the control not gate. So before we're dealing with a single and there I talked about the gate state zero uh, from Godwin's linear algebra. He was representing I hat and J hat 0 and 1. That is the gate state 0. So we have when we're dealing with 2-bit system. So this week we're dealing with a 2-bit system. Previously, last week we're dealing with just 1-bit system. So it can be represented by this equation A.
Uh, Ian, are you still around? Okay,
Mm,
I think yeah, we push it to next week.
yep,
All right,
possibly.
have a nice weekend.
All right, you too.